What's wrong with federated?
I don't know. I think they just want to
You
use
have Baptist in it?
No. Yeah,
For sure one, hopefully two.
First
40 years ago. 40 years
It's
ago.
non-denominational because it's like a bunch of
Sweet, heat oxidation reduction, excellent. Maybe even nuclear chemistry.
Wait, what chapter?
What
Eight.
you're in?
What?
Was nuclear the second chapter?
Nuclear would be the second chapter.
What chapter was the final last year? Like, it's just around chapter test.
I think it was over 17. So we're all quite a bit ahead.
Oh,
I'm gonna read it. Wait, we get the final of this chapter. I'm okay with that.
No, not this
Or are
one.
we doing a
We
We're
have
doing a one chapter
three more
or
Mondays.
No, I don't.
We're doing class 1 at senior
If
retreat.
it's over titration, they'll actually cry.
Oh, I do titrations was the only thing I got right on.
That's this coming Monday.
Dude, so that was, I did none of the
This
right.
chapter. But sure, you have easy chapter next.
Wait, so this test was their final?
Last year.
Well, I mean, like, if you study for it, like,
Look at
what's
this chapter.
Yeah,
This is an open test. We study way more than fine.
Okay.
What's the connection?
Everyone open up to 798.
You could actually. Oh.
Okay, we're just going to read this page. Hopefully we'll put the finishing touches on what change in G means, and hopefully be able to connect the change in G information from what we know about the rates. So 198, please. 798, please. Sorry. Okay, everybody there? Nope.
Yeah.
Hey, it's usually Emily. What's going on? Emily, you're having a good day, I see. You enjoying play practice?
Yesterday.
Yesterday you did what?
They blacked out for fatigue. Made it look fat.
Made you look fat.
Here, made it look old.
Okay. When the components of a given chemical reaction are mixed, they will proceed rapidly or slowly. Why does it pick and say it says rapidly or slowly? When we're talking about favorable, doesn't mean it's fast or slow, because there's kinetics that we are a big part of it too, right? Rapidly or slowly, depending on the kinetics of the process, to the equilibrium position. That is, I think if I woke up to that, I'd chuck it out the window.
That's my mom.
That's like grandma's ringtone.
What was that? A phone call? Okay. Back at chapter 13, we define the equilibrium position. Okay, in chapter 13, we define the equilibrium position at the point at which the forward and the reverse reaction rates are equal. Okay? In this chapter, we looked at equilibrium from a thermodynamic point of view. And we found that the equilibrium point occurs at the lowest free energy possible or available to a particular system. Okay? As it turns out, the two definitions give the yeah. So where you have the lowest free energy possible is the same spot where the forward reaction rate and the reverse reaction rate are equal. And it should. Which must be the case for both the kinetic and the thermodynamic models to be valid. To understand the relationship of free energy to equilibrium, let's consider the following hypothetical reaction, where 1 mole of gaseous A is initially placed in a reaction vessel at a pressure of 2 atmospheres. The free energies for A and B are diagrammed as shown in 17.8a. Everybody see A on the left there?
Yes.
Okay, it looks like GA, or the reactant's free energy is higher than the product free energy. So just based on that information, okay, which way would you expect it to shift? Okay? And the reason why is because if you go to the right, you're going to be going to a lower state of free energy. But as you shift to the right, what you're going to start seeing is they're going to start changing. Okay? As A changes to B, the energy for A will decrease because pressure is decreasing. And if you look looked up at the equation, you would be able to understand why that is. Okay? In contrast, free energy of B will increase because the pressure of B is increasing. The reaction will proceed to the right as long as the total free energy of the system decreases. At some point, the pressures of A and B reach the values where they are at equilibrium and make GA equal to GB. The system has reached equilibrium. Since A at pressure of A, this is where it gets really wordy. Okay, I'm going to go after this. Says the system has reached minimum free energy. There is no longer any driving force to change A to B or B to A. So the system remains at this position. Pressures of A and B remain constant. Suppose that for the reaction, for the experiment described above, the plot of free energy versus mole fraction of A reacted is defined as shown in the figures below. In this experiment, the minimum free energy is reached when 75% of A has changed into B. The pressure of A is 0.25 times the original pressure. So you can see if you have if you haven't reacted any of A, if you look at that bottom graph there in A, if you haven't reacted any of it, okay, it has a high free energy. I don't know if you guys can see this. So if you look at this visual down here, it says fraction of A reacted. So 0 means none of A has reacted. Does that make sense? Okay, at that point, if none of A has reacted, it's got a relatively high free energy. Okay? But then as you react A and produce B, the free energy what? Starts to, did I lose you? Once you start reacting A into B, what happens to the free energy? Based on the graph, on the bottom, goes down. Okay? Right, so you see this here? Everyone's eyes up here so you can follow. Okay, this is where none of A has reacted, 0. Free energy, as you on the y-axis, goes up. Okay? So the highest free energy is when A has not reacted at all. As A starts to react to produce B, the free energy drops until it reaches the equilibrium point. Okay? If you were to go beyond the equilibrium point, you would see that the free energy would rise. So, did this go all the way to completion? No. Okay? It went to the point where the free energy was the lowest, which happened to be when 75% of A reacted into B. So, depending upon where I am within the reaction will determine whether or not I'm going to shift left or shift right. If I have mostly products, I'm probably going to shift a little bit left. But if I have mostly reactants, I'm going to shift a little bit right, depending upon what conditions I have. Okay? So, since this is the equilibrium position, we can use the equilibrium pressures to calculate the value for K for the reaction in which A is converted to B at this temperature. Okay? I'm not going to continue reading because I'm just going to end up reading a whole bunch of variables, and it will probably not make as much sense. It would make more sense if you read that yourself, if you like. So, what this whole thing is we've been spending quite a bit of time talking about Gibbs free energy, and it's just the free energy available to a reaction, and a reaction will appear to stop, or you will see no change, when a reaction reaches its lowest free energy possible. That is also the point where the rates are, what? Equal. So they both agree on the same point. So an equilibrium point is when you have your lowest free energy available to a particular system. Not always does that mean completion. Not always does that mean forward favored. It could mean reverse favored. It could mean a lot of things. Oops, wrong way. So, what I want to do here, we're still using the equation that we dealt with yesterday. That guy. Okay? And we have two different sets of pressure conditions. Okay, and we're going to figure out, what do they want us to find? predict the direction in which the system will shift in order to reach equilibrium. All right, so let's start with A. Then we got 1 atmosphere of NH3, 1.47 of N2, and 0.01 atmospheres of H2. Okay, what do you think we should do first? Okay, find Q. Yep. We want this, right? Because this is under standard conditions. Okay, we're not under standard conditions. Those are not standard conditions. Does that make sense? So, we're going to find change in G. Probably the first place to start is to find Q. The next thing would probably to find this. Okay, so let's find Q. How do we do it? Okay, write the equilibrium expression, products over reactants. We got pressure of NH3 squared like that. I want you guys to plug in and solve for it. What'd you get? Yep, it is. What'd you get?
680,000.
180, right? Okay, now, if we knew K, we can figure out which way it shifts from knowing Q is greater than, less than, or equal to K, right? But we don't know K in this context, so we have to find it out a different way. They gave us the change in G at standard state, okay? So we can find our change in G under these conditions. All right, now, I'm going to convert this to joules because if you remember, our R value was in joules. Do you remember that?
3.5.
There's your joule number. Okay. 8.3145 joules per mole Kelvin. Our temperature needs to be in Kelvin here, so that's going to be 298. And ln of Q. Somebody solve for just this portion here. So if we rounded that, that'd be 33,300, right? So Kelvins cancel, joules per mole. Okay? So when I plug this in then and finish solving, what is our change in G? 0. What does that tell you? What should that scream to you right now? answer the question, we would say no shift.
Is that because you're wrong?
Yeah, but again, remember, if it were to be that small, we're going to assume that,
It's negative 24.
yeah, that's, yeah. So if I'm doing a problem like this, if it's close to zero, assume you're at equilibrium. The situations where you're not at equilibrium, I'll make it pretty obvious. Does that make sense? You'll have a large number, okay? Because just due to rounding, it's going to, you'd have to round perfectly to see that it would be zero, okay? So, this is when our equilibrium conditions are. So if we try to solve here, my guess is we will not be at equilibrium. So let's do that one. Actually, why don't you guys do that one? The process is the same, you just have a different Q. So you really can keep all of these numbers here, just change that one.
Well, it's all ones.
Oh,
One.
okay, yeah, duh. So this will then be ln of 1 is 0, correct? Ln of 1 is 0, which means all of this stuff will cancel out, and our change in G is so, which way is this going to shift? It's going to shift right because of the negative number. Products have a lower free energy, so it will shift right. If that were a positive number, it will shift left.
Could we know that based on pressures that will shift? Because of the edge. No, never mind. Never mind.
What was that?
Never mind.
Okay. So, thing that we want to be able to grasp here is what a change in G of 0, greater than 0, or less than 0 mean from a particular standpoint of the reaction. Are we at equilibrium? Are we at a point where we have to shift to the right to produce more products to get to equilibrium? Or are we at a point where we have to shift to the left to reach equilibrium? Essentially, what we want to know is, if we had a free energy graph, where are we on that graph? Does that make sense? If we're right here, we're going to shift right. If we're right here, we're going to shift left. If we're right in the middle, our change in G is 0, we're not going to shift either way. Okay? So, we can then do this next problem. We can predict what the K value is going to be if we set our change in G equal to 0. So, same equation here. But if I say this is 0, then this changes to what? If this is 0, we're at what? Which means that needs to be
Ones. No, it can't be one.
it could be. No, well, it probably won't be.
No, the whole thing has to be the positive of the negative.
When we are trying to figure out equilibrium, we usually write what expression? With what constant? If we're at equilibrium, then we know we are at our K. Q, right, if we're solving for Q, we don't know if we're at equilibrium. But if we're at equilibrium, we have our K. So, what I can do then with this logic is, if I know equilibrium is where you have no change in free energy, or your free energy is the lowest, I then can figure out what the K value is for a particular reaction if I don't know it. It's a different way of figuring it out. So, what we are going to do here is we are going to figure out what K is. Now, we have a little bit of work to do because we do not know this. So if I were to rearrange this, your change in G is negative RT ln of K. Because the zero's out of there. Make sense? Then we need to find this, and it tells us to find it how. For the sake of time, I'll just give it to you. How about that? I'll give you that. I'm not giving you 10% of that credit.
You do have one.
Bet. What if you have to?
No, he has to.
He really is in some way to get rid of that though. Like,
But the thing is, you can't, because one person is
So
buying.
what, yeah, so what?
It penalizes them for not paying.
that's true, yeah.
How about if I don't buy one?
I will sign a petition.
No one's
Oh,
gonna.
no one else will.
No one
I'm
else
gonna go to
will.
all the parents and say, this is hurting your children.
This is
You're
how.
gonna go to all the things.
But they get it with color.
Open houses are open.
So sort of consequences.
Why won't a student stand up for their own education?
Because we're graduating.
Why won't a student say, you know what, Mr. Kramer, you're right. What they're doing is wrong. It's just teaching us laziness, irresponsibility, and bribery.
Yep. We're not disagreeing with you, we just want the grade.
All right.
I mean, I don't know.
Who will stand up and fight for education? Who will stand up? Dilly dilly.
Give me a Bud Light.
I mean, oh, you can't post this in video now.
Stop.
That's on video, dude. Hey, Mr. Williams. You said dilly dilly at Christian school.
Stop. I don't even know what that means.
Sure, you don't.
You're the one doing commercial. Does it actually mean something?
Yeah. No, it just it's just like it's just it's been around for.
It's just been connected to, yeah. Okay. So, we need to actually find,
That really wasn't the correct context to use it.
I know.
It really wasn't.
But it was a great speech. But also the words in it, so.
Yeah, that's the goal. All right, so I gave it to you in joules. Okay, normally these would not be in the same unit. Does that make sense? Usually kilojoules is for change in H, and joules is for change in S. So I already did that for you. Don't forget that on a test, because I guarantee you one of the multiple choice answers will be the ununit converted answer. Okay, so you'll think you're getting the right answer when you're not.
I was so good, but I don't want to
Right. I'm still waiting for the day that a student will stand up and say, you know what? I value my education. Even though the school doesn't, I value learning.
That's on camera as well. The school does not value education. Some kid from AC is going to find us on YouTube. See, you're missing middle school for next year. Grade 1.
Okay?
Hey.
I will be pushed out, joining the ranks of a fellow teacher that died this year. Change G. Another teacher that got canned for having strict standards died.
Oh my god. You want to be in that category. And that wasn't because you had strict standards.
Well, we like you.
Just
Oh,
your problem.
I know what you're talking about. I think you're talking about just some random teacher. Sorry, guys. This is why I gotta be in her class. Hey,
Right.
Hey, if she was still here, I'd.
Okay, we're done, guys. We're
I'm
done.
using it on history. Don't worry, Kramer. I'll use it on history because it's my first high school being. I'm salty about it.
Is true, Mr. Fisher?
No, with Miss Stoker, I gotta be honest. Dude, I had better grades.
What are you salty about that? Did you learn more or not?
No, I actually learned more than her.
I learned
I didn't learn any more, and I got a worse grade.
teach. That was the problem.
She did. She
didn't say, hey, just read the book.
All right, all right,
She
all
taught
right,
history.
all right, all right. Now that we got change in G, try.
4.
Okay, so 1 equals to our R. Our temperature what, 298? Now I'm with K. So we have to divide and then e to the answer. So what K ends up being, I'm going to severely simplify this. Okay? Ends up being e to the 601, which,
Why
yes,
is it negative 8?
because when this is 0, we had to move this to the other side. So it becomes negative. Does that make sense? Okay. So your calculator isn't going to even compute this. It's so huge. You remember situations where the K was so big that we couldn't even compute it? Okay. So we can assume that this particular reaction is probably going to go all the way to completion. Okay. So I would say this is very thermodynamically favorable. Questions? What a great day.
I get a copy of that.